Okay, so here we go for the second lecture of PDFs. So today we're going to talk more about practical things, how we do things. So yesterday we covered definitions and stuff. You heard a lot about theory from Pavel's side, and now we're going to explain, it's going to be more practical, how things are really done. So I asked some of the students who are here, the one I knew, so what they wanted to know, and they told me, how do the PDF really go into the cross section, and how do we compare them with that? So how do they really enter the game? So we're gonna really spend some time on that. Okay, let me see. Okay, so that's for today. This one. Okay, so I took inspiration from my colleagues from CT. Okay, and disclaimer: I don't put any reference, so I can update it later in case you guys like on the slides. Oh, thank you. Because there are too many references, and I'd rather spend some time doing the slides than putting the references. But if you guys want references, I can update the slides in the future. Okay. Okay, so that's just, we're gonna start with just a few simple slides, okay? They're not gonna be the full game, but just a few ideas to get the concept, right? So I took that from Pavel, okay? By now you should know it. So we start with DIS, it's just like an archetype process to access PDFs, but as we've heard, there are many, many more. And so that we take this archetype of PDF. So you have the left-hand side, differential cross-section, and on the right-hand side, you have the PDF, the Platonic cross-section, okay, the convolution of those two, plus corrections, okay? So, in a nutshell, left-hand side, experiments, right-hand side, theory, okay? So we get data here, so I put we have data for that. I call them D sub I, where I would be some, in that case, we have some value of some average value of Q squared and X, okay, given I, okay? So I will have something discrete, say, and on the left-hand side, I will have to match, okay? So I will have to evaluate this one. So that's what Pavel discussed yesterday, how we evaluate all those things, blah, 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 and convolute with the PDF, okay? That is unknown. That's the idea. So you have this theory prediction that is a really, I try to be comprehensive. So T is for theory, okay? So X Q squared, a PDF, and that's a set of vectors that I call P, okay? And I will explain what they are. So P, so underline is vector, okay? The vector P will be the parameters, say, of that we take into account here, standard model, whatever parameters we need to take into account. F1 AH is the PDF, okay? And X Q squared. Notice that so far I've not put any sub I index. Of course, we will have to go into the sub I to match the kinematics here, okay? So that's the idea. So we need to express the observable in terms of the PDF and the cross sections that we can calculate in given kinematics, right? So that's what it means. So that's left-hand side data, right-hand side theory. Okay. So the point is that the PDF is an unknown function of f, capital F, I called it, that depends on some parameters A. Okay, that's a vector of parameters. So the theory prediction can be written as depending on X, Q squared. There will be other kinematics as well, like Y, other things, and a set of functions that depend on parameters and the parameters of the standard model that we use. Okay, and so those functions are unknown. We select them, we choose them. Okay, and so that's that. Then on top of what I've written here, the data, of course, have some uncertainties. So you would have here, so like a set of central values or average values. Then you would have statistical uncertainties, systematic uncertainties. Sometimes they are correlated as well. Okay, sometimes they're uncorrelated. So there will be a bunch of things. Sometimes they give us a likelihood. Okay, so those data don't come just like that. They come with uncertainties. Okay, and then the whole game is to find what is the set of functions that depends on some parameters that describe the PDF that leads to an agreement with the data. Okay, then we have to define agreement, okay, and all those things. But the idea is how do we find a set that would describe the PDFs such that the right-hand side agrees with the left-hand side, okay? Is that clear to everyone? Yeah? Any question? Not yet. Okay. Okay, so how do we do that? So to do that, we need to define first what we call as agreement, or we define the concept of distance, metric, loss functions, objective functions, and things like that. So there are two different things. So there will be objective function, and then after we can define what's called the distance between what we find and the reality, okay? So we define an objective function, which is usually a chi-square, or it could be a likelihood. So the chi-square is also called the log likelihood, okay? So this chi-square will be minimized, okay? We need to find the experiment, I guess it will be the minimum of the chi-square that will give us solutions for this problem, okay? So we define the chi-square, which is data minus theory squared divided by, that's a really schematic way, okay? Then I will give you exactly the one we use, divided by the uncertainties. Those one will be the uncorrelated ones. And then you have other things coming up, like penalties. There will be something coming from these systematic correlated uncertainties and all those things. So the idea is that to find solutions, we need to minimize, okay, so minimum problem, data minus theory squared. And here, I already took the average over I, okay? So we do that for each experimental point for each experiment, okay? So this sum accounts for all the data points of each experiment, okay? And you do that, okay? Then you will see how many data we have, okay? So we have not talked yet about the dimension of those vectors of the parameters and stuff like that, but if you just take one dimension, okay, the chi-square respect to the parameters will give you in one dimension a parabola, okay? And then you have your best, the chi-square minimum, you have the best fit, and then you see the beautiful parabola, symmetric. It doesn't happen like that in the real world. And then you can define the uncertainty, okay? So that's the basic idea. And then, of course, it gets more complex because we're going to go to really high-dimensional spaces, okay? So to do that in real life, in global analysis, where we have more than 4,000 data points, in the case of the unpolarized PDF for the proton, it becomes a bit more complex, right? So you have experiment theory and statistics. So you really have to combine all three to get something that is robust and really solid. So the main groups for the global analysis of the unpolarized PDF, I apologize if people come from other groups, is CT. So here, CT is actually comes from MSU, MSHT, and then PDF. There are other groups who care about other PDFs, TMDs, many things. So JAM, CJ, a map, other groups, okay? So I took that scheme from XFeater. So XFeater, if you want to know more, I think you know about XFeater already, right? Because you had the tutorials, okay? Wonderful. So XFeater is based on min-width minimization, okay? So that's the same scheme as I showed you before. So on the left-hand side, you would have the experimental data, the theory prediction, and then you really have different things. So you have PDF parameterization, which I told you about before, QCD evolution, the external routines, and you have to evaluate the theory, and then you do the QCD analysis, and then you have to choose, right? Every line here is a choice, okay? And then in principle, you should make more than one choice, okay? You define the function you want to start at the initial scale Q0, okay? So you need to define which scale you're gonna put your parameterization, okay? So you don't know, you need to infer a function. I'm gonna talk about that. But scales Q0, you need to define which scale framework you want to work with. So there are different ways of minimizing, of taking into account all the things you're gonna do. And how you treat the uncertainties. You do that, and then you get to the results and you see the implication, right? So we're gonna talk first about which data, then the framework, and then the result, okay? And you tell me if you have questions. So I took that from Pavel. I mean, I think everyone takes that plot from slide to slide. So as you will see, so we will have some benchmark data, usually DIS and other things. You fit the data, okay? So in that case, that's the scheme for one solution or one central value or one replica, and I'm explaining what it means. You get a PDF, okay? And that PDF, you predict other cross sections. So now we do have predictions, and also we use some LHC data as well, but that's the idea. So you get some benchmark data, you get the PDF, and then you predict what happens at LHC at some process, right? So you need the PDF at colliders to predict other observables. So that's, as I said, just you see one curve, it's just one solution. But as I told you, the uncertainty, what you see here, the data has some uncertainty, so you need to propagate the uncertainty of the data. And on top of that, there's also uncertainty coming from the methodology we use, right? So you do that for a set of solutions that leads to a distribution, and then you would have, of course, an uncertainty band, okay? You have an error band on the PDF and on the predictions you're gonna have, okay? So as Pavel mentioned before, nowadays, a lot of the attention we put into the PDF fitting is to determine this uncertainty band, okay? The error band on the PDF, and now it will affect the future observables or the observables in really in precision measurements, okay? So I will spend some time doing that. I can't tell you everything in 1 hour, but I'm happy to answer questions, okay? Okay, so there's always this, you've seen that before, I guess, this precision and accuracy. So if you play those games, you know that if you have low accuracy, low precision, you have this target here and you're all over the place. So you're not so accurate and not so precise. You can also be very, very precise. Okay, so all your events will go in one place, but it's not where they're supposed to go. So if you want to win, you want to be here. And you can have a good accuracy. Okay, so you're around where you're supposed to be, but not so precise. And ideally, what you would like is to be everything on really the center of the target, right? So that's the game, if you like, and that's the goal of many of the global analysis. We want to be precise, but we want to be accurate. We really want to make sure that the PDF, because we don't know the PDF, we want to make sure that our solution takes into account inside the set of solutions. We will have the true PDF, right? And I will tell you how we do that. Okay, so let's talk about experiments. So yesterday and on Monday, you heard about many DIS, so electron, proton, muon, proton, and other things in neutron currents, charge currents. Then there were PP and P bar and all those things that happened. So all will be really important. So that's the data coverage of CT18. So we are working on CT25, so that will change a bit, okay? If you want to know more, then we can ask Saib. I saw her here. Where is she? She's there, right? She's the expert in the new sets of CT25, okay? So as you can see, so that's the coverage in X and Q. So as we said yesterday, PDF depend on X and Q, or Q square, if you like. So here it's Q, okay? And there will be, of course, other kinematic observables, but that gives you a map of which experiments will constrain which region of X. So not the flavors yet, but so X and Q, okay? So it's difficult to read, but you can see that there are like patterns, okay? And the first thing you can see is that there's nothing here below because there's a cut. Here we go, okay? So there are two things that must be cut. So first, we need to make sure that we are in the DIS region, okay? So we said yesterday we need to have, so nu has to go to infinity, and Q square has to go to infinity. So infinity for physicists is a different concept than this difficult concept. So here infinity starts at 2GV squared, okay? Which is a pretty high scale, okay? The initial Q square we're gonna use is gonna be lower than that, okay? So we start the PDF Q naught, which is about the mass of the charm, okay? And which is about the same thing, okay? And then we have, no, sorry, it's 2GV, not 2GV squared. 2GV, yeah, okay? And then we have a cut to avoid the resonance region and the higher twist contributions, right? And that cut is on W squared. So if that's the invariant mass that we said yesterday of the finite state, if you have this invariant mass here, it's cut about 12.5 GV squared, okay? And that's the curve you can see here, right? You can just plot it. So it means that we cut on low Q square and large X, if you like, okay? And just to compare, so if you take a different cut on the W square, you would have much more data here from old experiments. So that's what some of, that would include some of JLab data, for example, okay? So those are the things that we have, okay? Then there are blobs. So of course, the area I drew, I just took the shapes. So they're not exactly covering, okay? This is a triangle. I mean, you could have contour shapes, but okay. So that would be more the DIS data, and that's you have the HERA data here covering most of it, and that's the area you cover. So that's really the backbone of PDF analysis. It's extremely important. and there will be an influence on the PDF analysis. Okay, then here you still have like DIS data, but the fixed target, and you can see that a lot of this region is actually cut by the W, the cut on the variant mass, and that will influence a lot the large X region. I'm gonna perhaps show that a few slides. That's important. And then you go to Drellian. So all the data were fixed Drellian here. You can see the blue points here, which is from Fermilab. And then you would have also the repetitive distribution of Tevatron, RIC. And in the future, there will be in CT25, there will be more of the LHC data as well. So in that region, you have Drellian, which Drellian that will go into W and Z production. Okay, sometimes you see WZ production, but it's Drellian that produce W and Z. Okay, this is important. And then that was supposed to be like a different shape, but I could not do it. Then you have the jet production, and in CT we have inclusive jets, and there will be more of this inclusive jet from the LHC that we'll take into account in CT25. So that's in that case there were about like 4,000 data points. I mean, you can count them if you like, and of course then you understand that this minimization becomes quite complex, right? We need to understand how it works. So before I go into the details, still in the data, that's that is expected sensitivity of observable PDF combination. So when you write the observable, the cross section, and all on, you can work out those relations, and you know which PDF matters at which X range, more or less. So that's what you guess. There's like educated guess of what you think those observable will constrain, right? And most of the time they do, but they also constrain other things. It's really an interplay of flavors and an X range and Q range, okay? Because we've seen that in Q, with the Q square, with DGLAP evolution, the PDF will evolve and will change, okay? So if you take the HERA data, that's what I showed yesterday, you have the structure functions here. Fixed target DIS, it's mainly F2P and F2D, okay, the one you worked out yesterday evening, remember? Okay, and if you take the ratio, you could constrain U over D, okay? You can also have a neutrino DIS for the strangeness and other things for the strangeness. If you take fixed targets Drellian, you would have D bar over U bar, that's for the photon here in this case. And if you have Z and W production, so production of Z and W, you can actually get U over D as well. Different X ranges, different Q ranges, but that's what you expect. Okay. Any questions so far? Okay. And then we see that it's not as simple as that. We would like it to be so simple, but there's an interplay of many things. Okay. So that was from the experimental side. So let's move to the theory prediction. So now the game is gonna be how to determine this function, okay, or this set of functions that depends on the set of parameters, okay, at initial scale Q naught. What are the frameworks we can use and how we treat the uncertainties? Just it won't be so comprehensive because it's too much material to say. Okay. So in the case of CT18, and I put some stars here because every collaboration has a different way of taking into account systematics, for example, and also some penalties that I did not put here. Okay, there will be different things that vary from group to group. So that's what I mentioned before. You have the data and the theory, okay, that depends on here a set of parameters. And then you also have the correlated shifts, right? So we have here the uncorrelated stat and syst uncertainties. And here you would have a matrix for correlated systematics, okay? And then you need to correct by a penalty for those shifts that you include here, and you see what happens. Then you need to minimize over the whole set of parameters. So in the case of CT18, it's depending. We have about 40 parameters, a bit less. 40 parameters from the parameterization here, and a huge amount of those parameters as well. Okay, so you need to minimize. So you can imagine that you are in a space of n with n large dimensions, and you're supposed to find a paraboloid in that space. Okay, you want to find this in a large dimensional space. Okay, so that's the main idea. Okay. And then you use a different code. So mean width is used in most of the cases, in the case of CT18, to find the minimum of the chi-square. Okay. Of course, the chi-square is not going to be as beautiful as this one. We would like to be that, but it's going to be a bit more fun, okay? And then you have this chi-square and you want to study, so you stay around the minimum, you find the minimum, okay? And you stay around the minimum to study what's happening, right? And you want to know what happens if you go up, if you go down, if you go in the vicinity and in one direction. So each of the directions will build it to a parameter, and you want to explore that vicinity of the minimum in this large dimensional space, okay? Why? Because not that you find, if you find this one, okay, so that would be more like in the Hessian framework, you find this one, that would be the one curve that I showed before, but you want to have a set of solutions, right? So you need to give uncertainty on that, and that's what we're gonna do, okay? So before we go into the uncertainty, well, we go in the Hessian formats. So when you take, I don't know if you see stats or if you do some laboratory work and you propagate the uncertainty of your measurement that you do in laboratory, you know that you can take, you have a function of parameters, and you that's how you define the uncertainty on the function, right? You take the derivative with respect to the parameters, the covariance matrix, and the other one, and then you calculate that, it gives you the uncertainty, okay? Now, if you want to do it a bit more practical and you want to do it in the case of PDFs, you actually can go from this covariance matrix to the Hessian matrix, which defines this. Okay, so that's the second derivative of the chi-square with respect to the parameters. Okay, and that works if you have small variations around the minimum. You stay in the quadratic approximation. Okay, you don't go too far, and you can do that. Okay. So now it's still a bit complex to understand how it works in large dimensional space. So what you do, okay, is that it's better to understand this way. You expand the chi-square in terms of the chi-square minimum of 0. The first one is 0 by definition because we are the minimum. And then the second derivative gives you the Hessian matrix, right? And that's the space that you would have. And those are the parameters A, okay? And if you are just two, you have one parameter AI, AJ, okay? And you have those ellipses, okay? You can just take one, but then you can multiply the ellipses by some factor and you would have different ellipses, right? And you have the minimum and you can find vectors. Okay, so that's the basis. But now if you want to be more practical, you can diagonalize this basis and go into this what's called the eigenvector basis, when you have circles or spheres in hyperspheres, actually in n dimensions, okay? And so you just have chi-square plus the sum of those vectors, the eigenvectors, okay? Eigenvalues. So you can do that. And now you can imagine that you have hyperspheres of those in that space, okay? And that's what you want to study. Okay, so that's what I said. And now the delta chi-square, okay? So imagine we have the delta chi-squares we had before, okay? But we are in n dimension, and they will basically be spheres in a space of the eigenvector sets, okay? You can just see that in that way. Okay, so that was again the picture we had before. We had this naive parabola in one dimension, and usually when you take the uncertainty, the way I showed before with the covariance matrix, and you don't do anything else, you define the delta chi-square equals 1 quaternion. That gives you 1 sigma. So here F would be say it could be a PDF or it could be a function of the PDF, but that comes from the theory side, okay, when we evaluate something. And the minimum here sits at F equals 2, okay? And then we can define the 1 sigma uncertainty here. That would be around 0.5 and then up to 3.5, okay? That's what you get. But then what we know is that there are many sources of uncertainties that take into account here. So that would come from propagating the uncertainty from the experiments, okay? But then we also have uncertainties coming from parameterization, and I'm going to talk about that. Some tensions between the data. So you could, in principle, say, oh, those data actually don't quite agree. So we have to take into account some larger space. And in real life, you would have more solutions around that kind of shape that are a bit shifting, and you have more than one solution. And then what you do is that you try to encompass all these tensions and all those solutions by including a larger a larger cut on the chi-square, right? Instead of cutting here, you decide that, okay, I want to take into account more things and more things have to be defined, okay? And then you cut, in that case, the chi-square equals 4, which is the example we have here. And what we call that is a tolerance factor. So we consider this 1 sigma uncertainty with a tolerance of 4, okay? So that's the difference. So that's basically what you do, okay? So remember, 1 sigma would be for the experimental uncertainties, okay? And the delta is equal 1. And when you increase the delta square equal to t square, then you account for more sources of uncertainties. And that's how we do it. That's the CT recipe, okay? So now, if you go to if you don't use the usual echelon propagation that you learned at some point, well, I hope you learned that. I mean, perhaps you don't, okay? Then you can also do something different, which is called the Monte Carlo method, okay? Or the bootstrap, or depending on how you want to call it, is that if you, for each of the data point that you have, okay, you have data point, uncertainty, instead of finding the central value of your feeds and propagating the uncertainty, you generate pseudo data, okay? You say, I have a Gaussian, my uncertainty is Gaussian, okay? And instead of having just one data point, I generate 100, 1000, whatever I need to do to reproduce that, okay? So I don't have one point in uncertainty, I do have a set of pseudo data or replicas, okay, of the data. So you do that in the data space. You just generate this density here, and then you do the fit 100, 1000 times, whatever you need to do, okay? That's what you do here. And in that case, the way you propagate the uncertainty is a bit different. So you can define a central value like the unweighted average, okay? And the deviation from the full set. But what you can also do is just take the set as it is, as a full solution of solutions, and study it case by case. So that would be an example of the distribution that you have from an MPDF from some given values, okay? So there are two different methods, as I said, that are used, okay? Sometimes they actually are mixed, okay? So the Hessian method is really, that's what it is by CT, CJ, MSHT, they've changed, okay? And then you would have that the central value is the function that you find. That's the one I showed you before. You have a central value at a minimum chi-square, okay? And then you can define the uncertainty. That's a master formula that goes with the directions of in the eigenvector space, okay? You can do that. In the case of the Monte Carlo, which is an NPDF, they're not the only one, but okay. And also Jam does that as well. And most of the TMD people do that as well, okay? Then you would have that the central value, you can define the central value as an unweighted average, okay? Which is not a solution of the problem. It's just by definition, it's a definition of something. And then you can take the uncertainty of the Monte Carlo, or you can play with just the set, okay? And see what you can do. So now it comes to, now we define the frameworks that we use. We're still missing, where is it? Okay, we're still missing the parameterization, right? The function f of the parameters, because a lot of the uncertainties will come actually from the function we decide to choose, okay? So first, as we mentioned yesterday, there can be some constraints on the PDF. Someone asked about positivity of PDFs yesterday. And so there are two classes of constraints that we have. Some will be what I call first principles. That would be sum rules, positivity of the cross-section or the observable if you need. And on the other side, we also have model or QCD-inspired constraints. So now you may or not like those ones, but they are used in many cases, right? So first we need to ensure that we have symmetries that are fulfilled, that we impose. We need to have different things like quad counting rules, for example, or wedge behavior. It's a large, a small x, but here we really have to first principle will be sum rules, endpoint, especially at x goes to 1. Okay, at the support of PDFs, it's put it on 0, 1. Okay, and that's extremely important. Okay, so it seems like basic to impose those things, but you need to find a set of functions that fulfill all those things and at the same time accommodate for the data, right? Okay, so there are, that's why we separate the problem. Okay, so most of the first principle, not all of them, come through a carrier factor. Okay, so that's what we call the carrier function of the PDF. And this carrier has the usual shape of normalization, okay, that can be fixed by some rules or other things, x to some power and y minus x to some other power. And those powers have to be constraints, okay? So those if you can imagine x to some power 1 minus x, it's like a bell shape, depending on the value of A1 and A2, okay? But those will ensure, if we really have the parameters in the right, if they turn out to be in the right value, range of values, that we have the asymptotic behavior, right? So really, we ensure here that we have 0 at the end point, okay? And we ensure that we have the right x behavior at 1, okay? But that's not all of it. So when you don't have a lot of data, you don't know what to do, you start with that. And of course, that shape does not change so much. So you need to, on top of that, you multiply that shape by what you call the modulator factor, modulator function, okay? And that modulator is usually a polynomial or a neural network. Okay, so I think there are two different concepts. So people usually associate Hessian formalism with the explicit parameterization of the polynomial here that we have, and the Monte Carlo as neural network. It's not always the case. So you could use Monte Carlo with fixed parameterization. There's no problem at all, right? But in the case of an NPDF, they have neural networks here. Okay, so that's a neural network with a lot of parameters and their corresponding optimization algorithm. So they have to decide how they define a neural network. But you can also use Monte Carlo formalism with explicit parameterization. That's what Jan does, for example, right? And other people, because nowadays it's easier to generate replicas than to diagonalize a matrix. Okay, it was not the case before. So many of the younger collaborations do that to start with. Okay, so that's the thing. So the function that we called before f of a is this function here. It's factored into a carrier, okay, that really takes care of the asymptotics and most of the first principle, okay, and a modulator that will change the behavior in a more or less flexible way in between, okay? That's important. Okay, so a bit of a fancy slide that I took from other people as well. So it has become like really, really more fancy nowadays to talk about inverse problem. So what is an inverse problem? Is a problem is from the data you need to find the underlying law, right? And there are many types of inverse problems. Some are more simple, some are more complex. But in most cases, like in 99 of the cases, the problem it's ill-posed, okay? So you won't have one solution and you need to actually, but that's the idea. You have data space and you take just one set here of data, for example. And I put an example. It could be a cross-section that we had, okay? And on the right-hand side, you have model space, okay? All possible functions that you need to have. They can be continuous functions, integrable functions. They have to be integrable as well, okay? And all those specifics that you need for the functions. And then you have this ellipse here, which is the set of functions that you try. You need to try a set of functions. But if you do the mapping, if you knew the mapping, okay, it would turn out that the mapping of this theoretical function would be this one here, right? So somehow the game is how do we find the true ensemble, the true set, knowing that we can only explore a finite number of functions, right? So that's the game, and that's why it's difficult, because we can only try a few of them, but you need to try a few of them. Okay, so that's the idea, to try to get the inverse problem. Okay, and in our case, it's what is called a convoluted, because we have convolution and it's also nonlinear. Okay, so those are toy plots. Some are not so nice. They're supposed to be smooth, but I was not able to make it smooth. Okay, so if you have a low initial scale, okay, Q naught, then you describe your function that way, okay? So the problem is not as simple as you think. We say, okay, you have to define, to infer the parameters. We don't infer only the parameters, we need to infer the function, okay? And that's not so simple. And then infer the parameters of that function, okay? So in the Hessian formalism, so I took that from Pavel, so that's a really nice cartoon. You would have a sort of function here. And as I said before, you have the data points with the uncertainty, you find a good fit, okay? In the case of the Monte Carlo formalism, you would have, here I put 5 replicas, okay? But you can put more, okay? And they're not really Gaussianly distributed because it was complicated to do it. But imagine that they are Gaussianly distributed, okay? And you have your replicas and you find good fits, okay? And also the set of replicas is to be split into training and validation sets, okay? You need to do that. So that's how it works. And okay, so what the good question is, what is the optimal parameterization? Okay, it's difficult to define, but then we need to have something that is flexible enough, and I can accommodate for data, but that does not overfit and fits the fluctuation. So if you take this example, it sort of comes from Pavel, you have a lot of points here, and you try with a degree 4 polynomial, okay, a simple one, and you see that you get this dashed curve, which seems to describe the data quite well. And you want to increase the degree of the polynomial because you want to try it, and then you realize that you start fitting fluctuations, right? So that blue curve is not what you want to have. You want to have something that is really stable and that has a low degree of polynomial. You don't want to overfit, and you don't want to underfit either, right? I mean, if you don't not flexible enough, then you don't you underfit. So we don't know what is the true PDF, okay? But what we know is that we can approximate any smooth, any function, a continuous function, by a polynomial, okay? That's the idea also of a neural network. They have polynomials of, well, some really complex, okay? But what you can do is that you can just take a polynomial function for the modulator, okay? And you can try a few different things. So CT18 uses Verstehen polynomials, because that's the basis you would have, okay? And MSHT uses Chebyshev polynomial, which are orthogonal polynomial in that case, okay? So that's something. Some other groups use less flexible polynomials, and depending on the problem you have, you can adapt a solution. But actually with CT, we have come with a better idea is to use an extension of the Verstehen polynomials, but it's called Bezier curves, right? I'm not talking about that now, but I can just show you a few things if you like. Okay, so then you want to compare to take, so once you do that, and I will show you the result, and if you will, you minimize, you have a function, okay, so you just take one function, you minimize, you find a minimum, and you want to define, to check if that function, you want to make sure that you really go back to the cross-section, right? So you do the minimization, you have the PDF, you plot your PDF, then you put your PDF back into the observable, the theory, and you want to compare with the data. So the distance of the theory description with the best fit PDF to the data is also a chi-square, okay? So that's not the one you minimize, but the one you use to compare with the data, okay? And then you can also visualize data over theory here. So that's for pion-induced Drellian. It's a bit different, but for the pion PDF, it stopped working. And so what you can see, so where you have data, this one is bigger, right? So where we have data, you can see that the grid pretty well, no problem, right? But then you say, okay, what if I take more than one parametrization and I want to compare also with different theory? And that's what is done here for a certain function from Drellian, pion-induced Drellian. And you can see there are 3 different parametrizations. In that case, the study is really large, okay? But all 3 are totally compatible with the data, okay? And when you see that with the data, I say, okay, so far so good, wonderful. But then what happens when I don't have data? Because as you've seen in the XQ plane that I was showing you, not all the space is covered, not all the plane is covered. So there will be regions where we don't have data, and we still have to get a PDF, okay? So there will be regions that are not well determined, okay, by the data, and that's what we call extrapolation region, okay? You will need to extrapolate. So it means that outside of this range, I could have functions that go in different directions, okay? And in principle, you could have that, okay? So that's important. So what we do in CT is that we use more than one parametrization, okay? Well, we will use in the future, okay? And so in the case of our CT18, that's the gluon PDF, okay? The uncertainty band divided by the central PDF. So that's why it's around 1, okay? So you take the central value, you divide all the uncertainty with that value, and then you get this kind of plots, okay? And you see that in this region, we have data, okay? And in the small x and very large x, there's not so much data. So you have a large uncertainty, okay? And that uncertainty can be understood if you use different parametrizations that go in different directions, that is not constrained by the data, okay? So somehow you can see that's what we do. So if you use more than one parameterization, you can do that. Okay. So just a toy model to give you the idea, okay? Focus on the cyan. okay, the cyan curve. So we have pseudo data, okay? We have a truth. So the truth is this red one, and we have pseudo data that were generated, okay? And we actually take the pseudo data with the uncertainty, okay? So if you do the Monte Carlo method, okay, what you would do is that you would, for each of those points with the uncertainty, you generate and how much? 50 replicas we use here, okay? So each of those one is like a bell curve with 50 pseudo data, replicas of the data. And you can do the fit, okay? And you end up with all those 50 curves that you see here in cyan. You see them? Okay, so that's the Monte Carlo propagation uncertainty, okay? So that's one thing that's really important. And you can see that it goes, the truth is encompassed by this those curves, okay? The truth is there, okay? What you can also do is that you can take the Hessian formalism, if you like, or whatever you like, and you can actually, instead of, so you don't use replicas anymore, you just take the central value and the uncertainty, you do the minimization, okay? And what you do is that you actually use 50 different functional forms, okay? 50 different parameterizations. And that's, you sample over parameterizations here. And what you find is that you have 50 curves, and there are those ones here. And you can see they're not quite the same, okay? So each of those curves here is a central value. And on top of each of those curves, you should have the uncertainty band, okay? So at the end, you need to combine this with that, okay? So that would be the 1 sigma delta chi square equal 1, okay? That you would expect. And accounting for this one as well, we account for different kind of uncertainty coming from the methodology, okay? And that's what we have here. Okay, let me go to the results. What's the time? 44, okay. So now you want to see the PDFs, right? Okay, so I showed you from the main groups. We don't usually show the PDFs like that. We show more the ratio to the central value to compare the uncertainties, okay? But I thought that would be easier for you to imagine the shape of the PDFs as we discussed it yesterday. Okay, so you have CT18 on top, MSHT, and then PDF. It's alphabetical order, right? So I'm not doing anything else. And so you see at a low scale, 2 GB, then it's 100 GB, I think. And here's a bit higher, and okay, you can see all they evolve, right? So this, I think I showed it yesterday. You can see the up here, the down, the gluon, strangeness, and you can see how they change, right? You see that the gluon is growing a lot. Same for MSHT, same kind of behavior. Okay, here they show the balance instead of the up. Okay, so it's U minus U bar. Okay, and you can see how it changes, right? How especially it's strange the gluon with the scale changes a lot. Okay, and then PDF also shows the balance here and how it changes. So you can see there is D gap is the same for everyone. Okay, I mean some parameters can change, but you can see the effect of how the balance changes and how the gluon changes with the scale. Okay, so that's the idea. These are the three main sets. Of course, there are differences in methodology in the data sets that are used and other things, and how they treat the uncertainties. Okay, so that's why they are all different. But you can see that there's a trend in the shape. Okay, so we want to check the impact. So I said before, we expect some things from the data set. So we say, for example, that what did I say? Drelian WZ production will give me some constraints on U over D. Okay, now we want to check if some of those is true. So there are a few ways to check. So remember the parabola I showed you before with the chi-square. Okay, so imagine that I said you can have a function f could be a PDF. So I choose this function f here to be the gluon at x equal 0.3 and the mass of the x. Okay, and that's a CT18 behavior. That's this beautiful parabola. Okay, that's what you get. But what you can do is that you can also plot this parabola set by set, okay, of the experiment. You say, okay, this data set, okay, and you want to check what how they contribute, okay. And so if you go in that direction, you check which experiments prefer an increase. So so that's the value of the gluon PDF, okay, at that X and Q, okay. And which experiment would like the gluon to be larger or smaller in that specific region, okay? And you can see those experiments here who have a minimum, like this one here, would prefer that, okay? And some others would prefer to be smaller, okay? So that's called a Lagrange multiplier scan, okay? It's a bit complex to do. And you can do some things that are much simpler to see many, because here we have one X and one Q, okay? But you can actually, you would like to understand what happens for many X and Q values, okay? So if you go back to the expansion that I showed about the chi-square, you can actually expand as well any observable, any quantity that depends on the PDF, okay? Could be a cross-section, PDF, whatever you like, okay? And you expand it. In that case, it doesn't have to be always, you expand it, okay? And you can define the uncertainty. So we go back to this orthonormal eigenvector basis, okay? And you want to see the gradient of that object along one direction, okay? And you want to see how it works. What you can also do is you want to check correlations between two different objects. You can say the correlation between y and x, and you have to define what is y and x, and then you will have the angle. So why is it useful? Is because you can choose x to be a PDF and y to be a chi-square, for example, and you can check what is called the L2 sensitivity. So you really check the correlation between the PDF along one direction, if you like, and then the chi-square. And it will tell you the sensitivity on this PDF, okay? So if I go back to this plot, you have the chi-square here, okay? And you want to check, so that's for one point in X, okay? So I'm gonna explain this plot. And here I want to have more than one point, but I have this point here. So I have X that goes from close to 0, then to the -5 to 0.9, okay? And I have the delta chi-square to sensitivity, which means that I check the sensitivity if I increase the gluon PDF, what would be the impact on the chi-square? Okay, so what you can see here is that this experiment here, CMS-HZ, the green square here, corresponds to this curve here, right? About here. Okay, so it means that the chi-square would lower, okay, if I increase. So as I increase the value of the gluon here, the chi-square goes down. Okay, you see this curve here? Okay, and what you can see is that I have a negative here L2 sensitivity, which means that as I increase the value of the gluon PDF, the chi-square decreases. So it means that this specific data set would prefer a gluon that is larger. Okay, then you can find if you take this one, it would be different, right? I'm not sure it's that. Okay, but. And then here we plot only the most sensitive ones. And so you can see for the gluon at 100 GeV, you can see which experiments are most sensitive to the gluon. You can see the different pools among all those things. Okay, so that's how you check if you really have sensitivity on what you thought you had. Okay, so you can do that for different things as well. So don't pay attention too much to what is written here. And what you can see different in different groups. So you have MSHT on one side and CT18 on the other side. And what you can see is that the different experiments will contribute differently depending on the set of PDFs, right? So it's not just the set of experiments that you use, it's also the methodology that you use, the functional form that you use, and all together you can see that the gluon PDF is constrained by some sets for one group and from other sets of experiments for the other group, okay? And sometimes they don't have even the same thing, right? They don't. So that's interesting to study. Okay, so now about the strangeness, you can do the same thing. So CT18 has more than one set. In CT18, usually S and S bar are taken to be the same, okay? And that's something that's being improved. So usually that's so you can, so that's S plus S bar that you can see here. And so if you only have, if you don't have difference between S and S bar, then you have this kind of pattern for the experiments that will constrain the strangeness, okay? So you can see that some of these experiments will constrain them. And then if you now allow to have a difference between S and S bar, okay, you will see different patterns that will constrain the strangeness. So the interplay between how you increase the number of functions that you fit the parameters that you have and methodology will affect the interplay with the experiments as well, right? So it's not just, oh, this experiment will give me constraints on U and D. No, they constrain the whole space of flavor combinations, okay? They will all interplay. Then you can do that too. So that's another plot. You want to do that for this. Remember that this plane that I showed before, X and Q, and you want to check which of the experiments that are, or the points that are on this plot can actually be sensitive to. That's the case. That's for the gluon. That's for CT14, another set with only HERA data. Okay, and you can see the really almost not so much sensitivity at high sensitivity where they are on the map. So you see that they are not just in 1 kilometer region, they are in various places of the plane, okay? Because they also come with the methodology. Okay, so I think I'm almost done. Final note, so how did the initial conditions for the hadron? So basically, when you put Q naught, you have initial conditions and you want to mimic what happens at low scales because it's non-perturbative object. You don't know this object. You want to infer it. And by inferring it, so you have initial conditions of a proton, okay? That we determine by tackling an inverse problem. It's kind of complex. What is the impact of knowledge of the standard model, right? Standard model being like from low energy QCD to other things, right? So from here to here, right? Basically, so we infer it, and then we also infer it here. We also have data at the LHC, but there will be also some conclusions. So a few things I want to mention. It's not comprehensive. So first, there is an exercise trying to understand the three groups together, trying to understand the differences of the groups, and to do that's a benchmark, and to also have a combination study. Okay, so that's called PDF for LHC. So there was the latest one was published 3 years ago, I think. PDF version 21. Okay, and if you can see, so that's the green curve. So it's a combination of the three sets we had at that time, which were CT18 with some modification, and then PDF 3.1 and MSHG 20. Okay, and that is made to help people at LHC to really have predictions that could be really useful. But if you really want to have precise measurement of some parameters of standard model, like really precise, you need to use each set separately, right? And there's an impact on PDF on the definition of some standard model parameters. And you can see here, okay, forget about CDF, okay. The mass of the W, that's made by the group that takes care of averaging the mass of the W, and how for each experiment, they made their estimates of the W mass and how it depends on the uncertainty depending on the group, okay? So what you can see is that the uncertainty coming from PDF, it's not just the PDF in that case, but how it will impact as well, the PDF, if you are precise and accurate, okay? The PDF has a strong impact on some of those observable, okay? So this uncertainty is not just the PDF uncertainty, but so you know. And then, of course, there's a high energy. There are many of those observables. So yesterday, Pavel mentioned SMEFT, okay? Many people want to find something beyond the standard model in whatever way possible. So, of course, they matter, right? I mean, the LHC would like to see if there's something else. But, as I said before, initial conditions will matter, okay? So if you think about low energy QCD, you can think about large X, as I said before, and there's D over U here. So there are three different groups and different experiments that actually fit. So CT18 will be here, the blue line, the blue curve here for D over U, okay, with the cuts that I showed you before. Okay, there's not so much large X. Then you have CJ. CJ has a lower cut on the W square, okay, and you have JAM that also have different cuts. So they include data that are more in the non-perturbative region, because they also want to fit some of the JLab data on the bonus and marathon data to get this ratio. And you can see that there was it is still not really known what is the uncertainty or what is the large X behavior of that function. You still have a large uncertainty on that, okay? And that's important because then you could have, in those cases, you need to understand the QC dynamics at low energies, okay? But then it's less clean observable. But that's important to understand both regimes, low energy and high energy, because they all go together. Okay, things that matter I have not mentioned. In-house developments, mini codes like EPAM, third-party developments for the analysis, many codes are used as well, like Apple grids and other things. Theory programs to go to entry-level PDFs, so that's important as well. All the complexity of the correlative uncertainties, or the things that we don't have time to mention, and things that I think should be your takeaway message, that determination of PDF in global analysis is an interdisciplinary field, so you have statistics, experiment, theory, all those things together. Precision against accuracy, okay? The space of solutions is large, okay? And that PDFs are crucial quantities for precision physics at hadron colliders. And I think that's it. Thank you. Yes.
I guess I'm kind of like curious, logistically, like, is you're taking data from like a lot of experiments. So I was like, wondering, like, is there a lot of effort that's been like looking at the data as like formatted correctly?
That's a good question, perhaps for Pavel. About the older data, I'm not sure, but the newer data, they come in the same format, right? Or not?
No, well, there is this big question which is related to the complexity of total uncertainties. Because each of these experiments will make up tens to hundreds of systematic uncertainties, and even within one collaboration, have multiple representations for classes of uncertainties and always the same measurements. So then it becomes very difficult to make sense of it. So yes, so there is lots of discussion going on right now, not to come together, but there is more work to do.
I think for the older data, before you could just go and download the things, but nowadays it doesn't work like that anymore. Yeah. More, yes.